In this video, I will be explaining to you about the volume occupied in different cubic structure, or in other way we can say like how to calculate or how to find out what is the total volume that are occupied by the constituent particle in a cubic structure. Why do we have to calculate that? One thing you have to keep that in mind, that because we are assuming the constituent particles are spherical in nature, and one thing should be clear in mind, that there is no other way you can arrange a sphere such that there will be no space left between them. There will be always a space left between them, always a space left between them. For example, just take a look here. Say you assume that the solid that you are talking about is containing four constituent particles and they are in touch to one another, as you've seen, because this one is the constituent particle are spherical in nature. There will be always a space between them. Likewise, supposedly you are assuming a simple cubic structure. Say I'm gonna draw this one here. As you all know, simple cubic structure. I'm going to take only the center of the constituent particle to get the geometry of the cubic structure. Here I'm going to take a simple cubic structure. In this cubic structure, what do you see? That there are 8 constituent particles. 1 2 3 4 5 6 7 8 8 constituent particle. In reality, actually this sphere is in touch to this one, is in touch to this one, is also in touch to this one as well. Here it means this way, right here. But there will be always a space left between them, always a space left between them, since this one is spherical in nature. Here, by this topic, calculation of the volume occupied in different cubic structure, it means that we have to find out in a simple cubic, or in a face center, or in a body center, what is the total volume that are occupied by the constituent particle, what is the space that are left between them. Remember, after we calculate, more will be the volume occupied, more efficient will be that particular structure, or more efficient will be that particular cubic. Okay, so first of all, I would like to start with what? I would like to start with a simple cubic unit cell or simple cubic structure. The first one, we will calculate the volume occupied in where? In a simple cubic structure or a simple cubic unit cell. Now first one, in simple cubic unit cell, in simple cubic unit cell. This is the so-called simple cubic unit cell. Here 1 2 3 4 5 6 7 8, there are 8 constituent particles. Please keep that in mind. Here I am taking only the center of the constituent particle. Here it is 1 2 3 4 5 6 7 8, there are 8, and you have to keep that in mind, that they are actually in touch to one another, but even though they are in touch, there is a space left between them. So here we are going to find out what is the total space that is occupied by the constituent particles. Are we clear? Okay, we are good to go. I hope we will proceed this one. Now in this cubic unit cell, or in this structure, I will assume that in this cubic unit cell, I will assume that the length of this unit cell, each length, anyone, you can take anyone, but as of now, I am taking this one. The length of this unit cell is a centimeter, a picometer, a meter, and so on and so forth. Alright, but here I will not mention the unit. You can assume any unit, a centimeter or a picometer, a Armstrong, and so on. Right, this is the length of this unit cell, and each of these sphere, this one, each of these constituent particle, you may assume this one, you may assume this one, and so on. The radius of this sphere will be r. You got this? Which means if I am going to take them separately, they will look something like this. Sorry, even though the sphere is not very proper. Center. This total will be the length of this unit cell, or the h length of this unit cell here. This whole thing will be a, and from this one to this one will be the radius of the constituent particle r. As you've seen from the figure, the edge length, that is A, will be equal to how much? Will be equal to twice of the radius. Are we good? Alright, edge length will be equal to 2 radius. Since these two spheres, they are in touch to one another. Okay. Now I'm gonna start this one, right? Solution. Here, my target is to find out what is the total space that are occupied by these 8 constituent particles and what will be the space left between them. Okay, keep that in mind. Now, suppose the edge length of the unit cell is equal to how much? Is equal to A. I have not used any unit here. You can assume centimeter, picometer, Armstrong, and so on. But mostly we use a smaller unit here, like picometer, Armstrong, and nanometer, and so on. Okay, not even centimeter. And then I will also assume the radius of the sphere. Remember here, this sphere represents a constituent particle. Radius of the sphere will be equal to how much? Will be equal to R. R centimeter, R picometer, okay? As we all know that the number of the constituent particle or the number of the sphere that belong exactly to only one unit cell in a simple cubic is equal to how much? Is equal to 1. We have find out. Number of sphere per unit cell equal to how much? In a simple cubic, remember, the constituent particle that are present at the corner is shared by how many? Is shared by 8 unit cell. And as you've seen here, there are 8 corner atom. I'll multiply by 8 corner. As a result, 1. So here, the number of sphere or the number of constituent particles that are belong to only one simple cubic is equal to 1. By formula, you know the volume of the sphere. What will be the formula for the volume of the sphere? Volume of the sphere is equal to 4 by 3 pi r cube. 4 is a constant, 3 is a constant, pi is also a constant whose value I'm going to take here is 3.14, and r here reflects the radius of what? The radius of the sphere, or you can say the radius of the constituent particles. You got that? Okay. Therefore, if I am going to find out the volume of the cube, how do we calculate the volume? Volume will be length into breadth into height, A into A into A here, because I'm taking each of these side will be A, isn't it? Say you can take the length, you can take the breadth, you can take the height. The side will be how much? The side will be A, isn't it? A centimeter, picometer. So likewise, if I am going to find the volume of the cube, volume of the cube will be equal to A cube, isn't it? Am I right? What will be the value of A? We have just find out the value of A is equal to 2 radius or twice R. So I'm gonna use here twice R. How much? Twice R cube. You got this. Now here if you multiply, you'll get 8R cube. 2 into 4, 4 into 2, 8. Cube of 2 is equal to 8. The cube of R will be R cube, isn't it? Therefore, I'm gonna find out the fraction occupied, or you can say the packing efficiency or the volume occupied. Therefore, packing fraction. You can also say packing efficiency. Packing fraction is equal to, I'm gonna write here. First, I'm gonna use a formula. Here you have to apply another formula. Like this is the formula we will be using in order to calculate what? In order to calculate the packing fraction or packing efficiency. You can also say volume occupied in a unit cell. The formula used here is equal to volume of the sphere. Volume of the sphere divided by volume of the cube. Volume of the cube. Volume of the sphere, from the formula, it will be 4 by 3 pi r cube. Volume of the cube is equal to how much? In this formula, in this simple cubic, we have 8 r cube. So you cancel this one and this one, and finally you will have here pi by how much? You'll have here pi by 6, which is equal to 0 0.524. Therefore, percentage occupied is equal to 0 0.524 into 100 will be equal to 52.4%. So as you've seen now in this calculation, in a simple cubic, the total space that are occupied, or you can say the total volume that are occupied by a simple cubic, the total space or the total volume that are occupied by a constituent particle is only 52.4%. The rest, that is 47.6%, remain empty. As you've seen here, there are 4 constituent particles above the layer, 4 constituent particles below the layer. They are in touch actually to one another, but there is always a space left between them. The total space that is left between them is 47.6, and the total space that are occupied is 52.4, which means in a simple cubic, the solid that are formed in this kind of packing is not a very efficient, or it's not a very hard solid, since the space occupied is, since the space left is more.